Okay, in order to understand what needs to be done next, let's realize where we are, what we have achieved so far in this world of electricity, in this course, right? We so far introduced two ways of finding electric field. So now both of these approaches are equally strong, equally powerful, universal, right? So you can use either Coulomb's law with the probe charge to find electric field of any electrical system. And again, that can be applied for any system in any point of the universe, no restrictions. Or Gauss's law, again, universal, fundamental, you can apply it for any system. So basically, we can say, yeah, we know now how to find electric fields of any system. Then, but it's not the whole story. Then we also introduced the fundamental equation for the electric force. F equals charge Q times E, electric field. It's another fundamental equation, basically, which allows us to describe interactions of those fields which we can find with the world, with material. Again, force, it's a quantity which describes interactions. So pretty much, if you know how to find electric field, and if you know how to describe interactions of those fields with the world, what else do you need in order to describe any possible electric phenomena in the universe? Nothing. Basically, what we just introduced and what I just reviewed, mentioned, it's called the foundation of electricity. Once you know that, you can say, I'm the king of this world of electricity. I know how to describe theoretically. Of course, it can be from the mathematical point of view, it can be ridiculously complicated, right? But theoretically, you can say, yeah, I can describe any electric phenomena once you know this. So pretty much now we can say, yeah, we are expert. We know everything about, we have foundation. We can solve any problem. Okay, so now, what is, yeah, you can buy a t-shirt like life is good, right? And you can enjoy your life just applying your foundation to solve some practical problems, right? Okay, so now, what is usually natural, normal response of any normal human brain at this stage when you feel like, oh, you are the king, you know everything about this, you can solve any problems. So what do usually your brain, or wait, what does usually your brain do in at a stage like this, in a stage like this? Your brain is very creative. You even doesn't have to, you even don't have to I don't know, train this creativity. Just by nature, our brain is very creative. It will start thinking, how can we simplify our life? Thinking, maybe there are some easy path, maybe there are some shortcuts, right, to achieve the goals, to solve problems, right? It's normal. It's like at the very beginning of the semester, you guys do the same, right? So first, at the very beginning of the semester, you're nervous, right, about new classes, new professors, right? You don't know them. But after a couple of weeks, you can say, this course, it's a Mickey Mouse course. I'm not going to attend that. Forget it. I'll just go to the final exam and get my easy A. This, okay, maybe I will come at the end of the classes to check attendance or so on, right? This, okay, this tough professor, I better go and attend the class and pay attention, right? So you start finding easy solution, right? Because, and especially in terms of mental activity, brain activity, it's a very energy consuming, right? And that's why it's easy. That's why it's difficult to force ourselves to do any brain activity, because it requires lots of energy, right? So of course, there is a natural desire to sneak, to find easier ways. So now we are at this stage where now we feel comfortable in some region, and now our brain starts thinking, what can be done to make our life maybe a little bit, maybe significantly easier. So now this is sort of like a philosophical introduction to the next reasonably big section of this course. In a few minutes, you will understand which approach I'm talking about. of course, you can ask me, do we have to develop this sort of alternative approach, making our life somewhat easier? Do we have to do it? No. If you don't like this easier way of solving problems, you can go back to your electric field and electric force and apply them. You can solve any problems. But most of people will start searching for easier solutions, right? So pretty much now our goal is find these sneaky ways of solving problems. Right? So, and now what is the idea? So what actually we have to do in order to make our life easier in this world of electricity? So, and basically that's why I created this picture, basically describing the major idea of next section of this course. So it's chapter 25 and the idea. So how can we simplify our life? Okay, so as I just mentioned to you, or reminded, so we just introduced two major quantities, right? This is the electric force, right? Okay, I used the expression for, probably I need to change this. But anyway, so electric force and electric field. And as I told you, once you know how to find them, basically you know everything about the world of electricity. So what's the common feature of these two quantities? They are both vector quantities. And again, it's not bad. That's their nature. We introduce them as vectors because in order to describe what we observe around us, right? It's like velocity, right? So it must be a vector quantity because it has a direction and it has a magnitude, right? So you cannot do anything else, something else, right? So again, nothing wrong with them being vector quantities, right? From the fundamental point of view. But at the same time, there is but, right? You remember the first lecture and then the second lecture when we had to add two vectors. First, two electric forces. You remember, to find the net force acting on the point charge. The next class, we added two vectors to find the net electric field at a certain point. You remember how much time we had to spend? Even here on the whiteboard, I spent like 15-20 minutes to get through that algebra. It's a straightforward work, straightforward. Well defined, we all know how to do it, but at the same time, it's so tedious, so boring to deal with these vectors. Really, right? So whenever I have to do something like this, it's not very encouraging, right? Especially imagine if you have not just two vectors, but what if you have 3, 4, 5 vectors? It's really depressing. Of course, now you can write a software, right, which can do that for you. But of course, we're discussing just without including software, right? So dealing with vectors is not fun. As I said, sometimes can be just depressing. So now, as a result, I told you, so your brain will start thinking, if it's so not pleasant to work with vector quantities, what can be done to make our life easier? Can we somehow sneak and simplify our life? And the idea is this. Can we introduce two new quantities? Scalar quantities. Again, you remember scalar quantities, they don't have directions, it's just numbers. One scalar quantity instead of electric force, and one scalar quantity instead of electric field. And of course, those two new quantities must describe exactly the same thing. If, for example, electric field describes electrical aura around a charged object, right? Charged system. New scalar quantity must also describe this electrical aura around the charged system. We cannot just grab, for example, volume. Okay, the volume is a scalar quantity. Let's use it instead of electric field. No, it's nonsense, right? Again, you need to introduce the new quantity, scalar quantity, but that quantity must describe exactly the same thing. So basically, that's what we want to do in order to simplify our life in this world of electricity. So basically, we want to develop a new approach to solve problems instead of dealing with vector quantities, electric force, electric field. We want to develop an alternative approach where we can use only scalar quantities. That's the goal, right? And we're going to develop this new approach for the next 3, maybe 4 classes. So it will be a reasonably big chunk of this course where we need to develop an alternative approach. Again, we don't have to do it, but it's a natural desire of our lazy human nature, right, to make our life somewhat easier. Again, nothing wrong with electric force, electric field, and you can still continue using them. But of course, their application is sometimes can be very time-consuming and tedious. Okay, so that's what we want to develop. And today we're going to introduce. Actually, what's the time? We still have, yeah, still 5 minutes. So today we need to introduce a replacement, a scalar quantity instead of electric force. And most likely tomorrow we will start working with introducing a new quantity, scalar quantity. That's the major point, instead of electric field. So today, instead of electric force. Okay, maybe some of you already realize which quantity I'm talking about, right? Maybe some of you still didn't realize, haven't realized it. Let me give you an introduction to the new quantity which we want to introduce instead of electric force. And in order to do that, I will tell you a fairy tale story. In physics class, fairy tale stories, right? Right, but first I thought that's kind of silly, but the more I used it, the more I like it, because it gives you sort of a feeling what that quantity, new quantity is. Okay, so imagine this fairy tale situation. We live in this fairy tale world. Okay, I live, maybe, for example, right? And there's a Lowell, there's Boston, right? And let's say in that world, laws, I don't know, organized by God, so that if I drive to Boston, from Lowell to Boston, for example, using, I don't know, first route, route 3, and then, I don't know, route 2. And let's say it will cost me $5. So I'm just counting money. I'm just greedy, right? Counting my money to travel. Then if I take, for example, route 495 and then 93, still $5. It will cost me $5. Or if I take a route, for example, 495 and then route 2, still $5. Or if I take I know, some local roads, right, small roads, still $5. And if, for example, I can take any route to Boston, and if every time it will cost me $5, then what will be the natural response of people living in Lowell? Since we can associate a unique number 5 with point where Boston is, of course, sooner or later we'll start, or some of us will start calling that like a $5 city, right, or something like that, because we can associate, we can connect a unique number with the point in space where Boston is. Okay, so it's interesting, right? So we can connect a unique number with that point. Then, of course, in a similar way, I can connect number, for example, 100 with New York, for example, maybe 500 with Chicago, I know, maybe 2000 with LA. So pretty much you see, now I can cover the whole map of this country with these unique numbers. And again, the key word unique, with which point I can associate a unique number. Wow, it's something interesting, right? Maybe it can be useful, maybe it can be ridiculously useful at these new numbers. So let's give it a cool name. Cool name is very important, right? In any research, especially if you want to sell it to some agency, right? So you need to introduce a cool name, right? Let's give it a cool name. And maybe some of you realize which quantity I'm talking about. for those who hasn't realized yet, potential energy. Let's give it a cool name, potential energy. That's basically how potential energy is introduced. We will get there, right? So now we're so proud of, okay, let's say I am so proud of myself. I introduced a new quantity to the world of physics, right? And of course, what do we usually do in that case? Of course, we go to our neighbors to brag about that so the neighbors would feel jealous or envy, right? So all right, so I would go to, for example, Andover people and start bragging. So I just introduce a new quantity, and number 5 is connected to Boston. And they would tell me, right, you know what, you big fat liar, right? So we're also smart. We also introduced this potential energy, but number 4 is connected with Boston, not 5. So how come that they insulted me and they have a different number connected with, for example, Boston, right? Because I measured my numbers, my potential energies, relative to which point? Relative to Lowell. Basically, that's my reference point where the potential energy is 0. Let me finish this fairy tale story and then we'll call it then we'll have a break. All right, because I measured relative to the Lowell. That's my reference point. But people in Andover measured their numbers, their potential energies relative to their reference point, which was or which is in Andover. That's their point where the potential energy is equals 0. So you see, whenever you introduce potential energy, you need to tell also people where is your reference point, where is the point where your potential energy equals 0. Otherwise, you're going to confuse people and they're going to call you a big fat liar, right? So that's how potential energy basically is introduced. But of course, I introduced in this fairy tale world where I just counted money, right? But in exactly the same way, we can introduce a normal potential energies in our world. And we actually, this world doesn't have to be a fairy tale world. We live in the world where there are examples like this. Let's introduce what is called a conservative force. And of course, it leads naturally to the idea of potential energy. So let's assume that we have some field. Gravitational field, for example, right? And of course, later on we can replace it with electric field. Oops, for example, I'm standing right here. I can draw gravitational sort of field lines, and this is situation. And so let's take a completely arbitrary 2 points, initial and final. So here you see initial point and there final point. And let's assume that we have some object, some creature, maybe balls, just this, which travels or is moved from initial point to the final point. And, for example, like that. And let's say that creature travels along this path. And you remember in my fairy tale story, I counted money, being greedy, right? $5. And now we need to count something else. Let's, of course, this object is going to interact with this, for example, gravitational field. Of course, it is going to experience gravitational force. And since there is a displacement, there is a force. We can introduce which quantity, which quantity, which we can count, for example, or measure or calculate work done by, in this case, gravitational force, as this object, this creature moves from initial point to the final point. You see, instead of counting money, I want to calculate the amount of work done by the force. In this case, for example, gravitational force. And if you recall physics 1, that's how work was introduced. In the most general case, it's an integral of dot product force and infinitesimally small displacement, f dot ds. It's physics 1, right? So if you apply this formula, of course, what is ds, for example, in this, okay, direction of the force, for example, right? I'm just making it, I just was making it up. It can be straight down, right? So it just, I try to be as general as possible. And ds, of course, will be that way. So you take a dot product of that, and then integrate from initial to the final point. Of course, you will end up with some amount of work. Let's say, for example, 5 joules. I like number 5. So it was $5. Now it's a 5 joules. Let's say a 5 joules. So then, if, for example, this creature takes a different path, for example, take this path, next one, instead of that one, and let's say work is still 5 joules. Again, you can calculate the same integral, but now over this path. And let's say work is still 5 joules. Huh, interesting. But what if I take a different path? Calculate work, let's say still 5 joules. Maybe more complicated with couple of turns. Let's say this path. And again, if you calculate work, let's say still 5 joules. Maybe you can go to Alaska and then come back to the final point, still 5 joules. If work done by a force is path independent, you see, like in this case, it doesn't matter which route you take. Okay, this creature takes. And if work is the same, like in this case 5 joules, then this force is called a conservative force. Right? So in my fairy tale example, so I was living sort of in a conservative force in terms of money, right? So if work done by a force is path independent, that force is called a conservative force. And now as a result, look, so it doesn't matter which path you take every time you end up with 5. Then basically we can associate this number 5 with our final point. It's like I connected $5 with Boston, right? It's the same story, exactly the same story. And of course, so that will be 5 potential. And of course, we are going to call this new quantity as potential energy, right? So we can say that the potential energy at that point will be 5 joules. And of course, that potential energy is measured relative to the reference point, which is at the initial point. So that is our reference point, and where usually potential energy is 0, right? So you see, if a force is conservative, we can naturally introduce potential energy because we can associate a unique number with the final point. But what, for example, friction force? Can we introduce potential energy associated with the friction force? Even if I pronounce it friction potential energy, it sounds so bizarre, so strange, so weird, right? Because of course you never heard that. And of course, we cannot introduce potential energy connected with friction force because work is not path independent. If you, for example, you have a flat surface, right? And if you start dragging some object from initial point to the final point, the work done by the friction force would depend on the path length. The longer path, the larger work done by the friction will be. So you see, you take a different route to the final point, and every time you will be getting different work done by the friction force. In this case, naturally, you cannot connect a unique number with the final point. Every time numbers are going to be different, right? But if you have this situation, yeah, you can have you have a unique number, and of course that number can be connected to that point, and of course you can call it potential energy. Fancy, cool name. So it's not unnatural, right? So only for conservative forces, potential energy can be introduced. And of course, so what are the examples of conservative forces? At this point, you should be able to tell me. It's a force of gravity and electric force, right? So both of these forces are conservative forces. And as a result, of course, you've heard a lot about gravitational potential energy, electric potential energy. Gravitational potential energy you used in Physics 1. And in this course, we're going to use electric potential energy, right? So what else should I mention? I'm trying to recall what else. Yeah, that's it. So now, next, before we start introducing formulas, which we have to introduce, and again, you remember what we're doing. We're trying to replace force, electric force, with a scalar quantity, which happens to be electric potential energy. Okay, now about the natures of potential energies. Let me ask you. Let's start with kinetic energy. You remember there is a kinetic energy, there is a potential energy. Kinetic energy, it is an energy of what?
Motion.
Most of you, yeah, it's an energy of motion. Kinetic energy, it's an energy of motion. If there is an object which moves, of course, we can introduce kinetic energy. Then, of course, logical question then, what about potential energy? Potential energy, it is an energy of what?
Position.
And position, yeah, that's what usually most of, okay, several times I heard that from students, and of course it's correct, but it's not, in my opinion, it's not the major things. I want to get sort of fundamental meaning of the potential energy. What you said is correct, but I want to get slightly different sort of view on the potential energy, right? Okay, let's start with the force. Force in general introduced in physics to do what? Because what we do, we just model. What we're discussing is just our way of modeling the nature which is created by God or somehow created, right? So we introduce force to describe what? And I mentioned already several times in this course, force was introduced to describe interactions, right? If if two people are fighting, right? So from the, I don't know, our point of view, social point of view, or criminology, right? So they're committing something, they're hurting each other, right? But from the physical point of view, they just exert forces on each other. That's how we model, right? Force this way, force that way, and no crime. They just exert forces, right? So force is introduced to describe interactions. These two people not fighting, they just interacting, right? And potential energy we're introducing to replace force, right? So potential energy must describe exactly the same thing. Potential energy is introduced to describe interactions. But vector force is a vector quantity which describes interactions. Potential energy, it's a scalar quantity which describes exactly the same interactions. Both of these quantities, force and potential energy, they both describe interactions of objects, right? But again, force from sort of vector point of view, potential energy from the scalar, it's a scalar quantity, right? And let me give you this situation. What if we have some point charge, right? And let's say I position it in an empty universe. So just point charge in an empty universe, there's nothing around. So what will be the potential energy of this point charge? Of course, it will be zero, because there's nothing to interact with, right? So since there's nothing to interact, potential energy will be zero. So you see, in order to introduce potential energy, we need to have at least two objects. Two objects, right? So now we're going to introduce two expressions, two formulas for electric potential energies. And of course, every time there will be at least two objects. Of course, at least there might be more than two objects. But reasoning to find the total potential energy in those cases, you will have to just repeat the same steps several times. All right. So kinetic energy, energy of motion; potential energy, energy of interactions. Right. Okay. So and now we still have a few minutes left before I start deriving formulas, and it will be probably next class tomorrow. All right. So let's juxtapose these two situations. Gravitational case, physics 1, and now electricity, world of electricity, to see similarities. And lots of similarities between these two cases, right? So again, let's recall in physics 1, what did you do? Let's assume that we have, okay, gravitational field, and the cat is falling down, right? Flying. Right? So how could we describe it in physics 1, or how could you describe it in physics 1? You applied usually two approaches. First approach, you can just grab gravitational force mg, vector quantity, right? And then and then you can combine it with Newton's second law, and after integration you can describe motion of this cat, or use kinematic equations if the acceleration is constant, right? So that was a vector approach to solve this problem in physics 1 using forces. But at the same time, since gravitational force, is a conservative force, and we just discussed what does it mean, what does it mean to be a conservative force. And since this force is a conservative force, in physics 1 you introduce potential energy, gravitational potential energy. You remember mgh, mgy, whatever position variable you use, right? And then you used potential energy in collaboration with kinetic energy, using conservation of mechanical energy. You could use that approach to solve this problem. That second approach is a scalar approach, right? So you dealt only with scalar quantities. So there were two approaches: either force approach, or vector approach, or energy approach, or scalar approach. That's what you did in physics 1, right? And of course, when you introduce potential energy, there was a reference level every time instructor asked you, and of course there was a potential energy at the point where the object is, and so on. So in our course now, in the world of electricity, we're going to have almost exactly the same situation, lots of similarities. Okay, let me finish this slide. Let me hold a couple of minutes. Will be very similar. Let's imagine that now, instead of a gravitational field, we have electric field, right? You see these green lines down, right? And this electric field is created by a parallel plate capacitor, PP capacitor, right? And let's assume that we have a charge is moving, right? So again, like here, you could describe the motion of the charge, like here, the cat, using two approaches. You can either use force, QE, and we've done it. You solved the quiz yesterday, right, and submitted using the force approach. Okay, I hope the force approach you used, right, QE, and then using kinematic equations like in your quiz, you can find position of this object at any moment of time, or describe velocity, or whatever, right, travel time. Well, now we are ready to develop a similar scalar approach, energy approach. Now, instead of force, since this force is a conservative force, we will be able to introduce electric potential energy. For this situation, in this case, we point charge, interact with the capacitor. So, of course, there is an interaction. There are two objects. Of course, we can introduce potential energy. And tomorrow I will derive this formula. And even compare the formulas. Here, it's a potential energy, mgy. Here it's a QES. Look at this formula carefully. M, property of an object, property of a cat. G, it's a gravitational field. It's a described gravitational field. And then Y, it's a position of the cat. Now let's look at the structure of this electric potential energy. Q, property of a charge, like M, property of a cat. Then E, property of the field, electric field. And then S is the position of the object. You see, the structures are extremely similar, right? So next class, we're going to derive this formula. And again, now we will develop an alternative approach to solve problem like this using energies, using scalar approach, energy approach, right? And then and then in physics 1, you had something like this. You remember universal law of gravity, Newton's law of gravity, G m1 m2 divided by r squared. That's the gravitational force. And again, since this force is a conservative force, in physics 1, you were shown that potential energy can be introduced. G m1 m2 divided by r. So you see structure very similar, but instead of r squared, you have r. Now, in the world of electricity, we are going to introduce similar, extremely similar. Instead of a Coulomb force, K Q1 Q2 divided by R squared, we're going to introduce electric potential energy. K Q1 Q2 divided by R. You see, lots of similarities. Almost we can say identical, right? Okay, so next class, I will derive this formula. This formula, of course, can be derived in a very similar way. I'm not going to do it, but we're going to discuss it and use it. So now we're going to introduce this and that and start using, basically, we are ready to start developing an alternative approach to solve problems. Instead of using forces, vector approach, force approach to solve problems, we're going to develop a scalar approach or energy approach. They're equally strong, equally powerful. Sometimes you can use this, it's easier. Sometimes this approach is easier to use. Force approach, energy approach. Okay, at this exciting moment, let's call it a day. And so the first system which we're going to discuss, charge, first object, capacitor, second object. So we have two charged objects, they interact. We should be able to introduce the expression for the electric potential energy, right? And since derivation is reasonably small, and to derive it we use some physics, some ideas from the past, right? So I decided to derive it, right, just to practice some stuff from the past, right? Okay, capacitor, and of course that capacitor creates a uniform electric field inside. Let me draw a few electric field lines, and you remember they start on positive charges and on negative charges. So I have to draw something like this, right? So this, and maybe one more. So these are our electric field lines. So electric field. Then I'm going to play with vectors, right, during the derivation. So as a result, we need to show coordinate system. It's very important to show coordinate system. So in this case, let me introduce this. And which S or X? S. Okay. For whatever reason, book uses symbol S, right? So that is origin. So the origin we're going to position at the negative electrode, and this is of course the spacing between electrodes D. Okay, so then you remember when we were introducing the idea of the electric potential energy, we calculated work done by a conservative force, and you remember you can introduce potential energy only if a force is conservative, right? Okay, we calculated work. So let's calculate work here as we move this charge from some initial point to some final point and see how we can get potential energy, expression for the potential energy. So let's assume that this is my initial position at this point. So let me label it as I initial, and this object, this charge moves to this point. So this will be the final point, F, right? And let me label their positions with this S. So this will be S initial, S sub I, and this will be S sub F. And as I said, let's calculate work done. Of course, there will be electric force acting on the charge. So and charge moves. We should be able to calculate work. And of course, you remember yesterday we refreshed the definition of work. You know what? I probably will write underneath. Yeah. So work equals integral of F dotted with ds. So dot product, scalar product of, in this case, electric force and infinitesimally small displacement. And of course, integral from initial point to the final point. Okay, so now let me show this vector ds on the picture. ds, so we displace that way. So this will be my d S. Right. Okay, and now let me play with this integral. So first of all, let me open my first explanation box, and of course electric force I can write as charge times the electric field. So let me replace, and of course charge is a constant factor. Of course any constant factor can be taken outside of the sign of integration, right? Properties of integrals. So I can rewrite this as Q integral from S initial to S final, and dot product now between the electric field and the displacement vector, infinitesimally small displacement vector. Now, look at the picture. Electric field points that way in the negative S direction, right? So you see electric field. ds that way. They are anti-parallel. Let's use this fact to take care of this dot product. Okay, I will open my explanation box, but I'm not sure that I can fit here. Okay, let me try. So electric field is anti-parallel, not parallel, sorry, to ds. So the angle between them is pi, 180 degrees, right? If you write this explicitly as E times ds times cosine of 180 degrees, cosine of 180 degrees is -1, so this dot product will be just a negative product of absolute value of E and absolute value of ds. Right, so, yeah, I cannot fit. So, E dot ds equals to minus E ds, right? Because again, angle is, okay, I will write underneath that theta is 180 degrees. Since angle is 180 degrees, so that's the origin of this minus. That's why this minus appeared, right? We've done it already in Gauss's law plenty of times, so now I can continue this line. So, and, you know what, let me first take minus outside. Then, what can we say about strength of the electric field? We are inside of the capacitor. Electric field is uniform, so E is constant. So again, we have a constant factor inside of the integral. Of course, that constant factor can be taken outside, can be extracted from the sign of integration. So we can write minus Q E and integral from S initial to S final of ds. So that's what we ended up. And this integral, it's trivial. It's an integral of dx. Of course, an integral of dx is x. And then you substitute upper limit and lower limit. So it will be S final minus S initial. So it will be minus Q E. And the difference between S final and S initial. Okay, so that's the amount of work done by electric force as the charge moves from initial to the final point. Now, let's recall from physics 1. Now we need to connect it with potential energy. So recall physics 1. Okay, you remember how work done by the force can be connected with, for example, kinetic energy or change in the kinetic energy. Most of you remember, right? It's called work kinetic energy principle, and you used it in physics 1 plenty of times. So equals to delta K from one side, but that we're not interested in this. But from the other side, if force is conservative, we can introduce potential energy, and in physics 1 you can also use the fact that in that case, work equals to the negative change in the potential energy. So from the other side, it is equal to minus delta U. So from one side, work done by the force equals to the change in the kinetic energy. From the other side, if force is conservative and we can introduce potential energy, work done by that conservative force equals to the negative change in the potential energy. So that's what we need, this part. Okay, so we need to use this. And now let me combine with this. So you see work, we just calculated. So instead of this W, I will use this expression, and it is equal to minus delta U. Of course, minuses will disappear. Okay, let me rewrite this. It will be minus delta U equals to minus QE and S final minus S initial. So minus, of course, goes. And let me write explicitly delta. You remember delta by definition, U final minus U initial. So it will be potential energy at the final point minus potential energy at the initial point equals to QE. Okay, let me write, open this bracket, QS final minus QES initial. Okay, so now you see that this term describes potential energy at the final point, obviously connected with this. And this term, which describes potential energy at the initial point, is connected to that. And you see the structure is exactly the same, QES. So now we can conclude that the potential energy expression for the potential energy when point charge is inside of a parallel plate capacitor is QES. So now we can write, so U equals to QES. Let's frame it. And now we can use this formula from time to time, or maybe I can say often. So what we have, Q, property of a charge, electric field, property of, or describes, let's say property of a capacitor, and S, position of a point. And remember, it is measured from the negative electrode. S is measured from the negative electrode. Sometimes, some book S can X is used, but this book uses S. It's not a crime. It's okay. Then what? Q is constant, E is constant, so potential energy is growing, right? Okay, linear. Let's say linear. Growing or going down, it depends on the sign of the charge. If charge is positive, of course, potential energy increases. If charge is negative, potential energy decreases, right? So as you move along S. Right? But you need to remember, when I told you that fairy tale story about the importance of the reference point. What's the reference point in this case? It's already inside of this formula. At the negative electrode. In this case, the reference point is at the negative electrode. Okay, where S equals 0. So let me check what else needs to be mentioned. Okay, probably I will just mention about the reference point. So let me write, so reference point. Basically, it's a point where U equals 0 is at the negative electrode. Yeah, difficult to write at the bottom of the whiteboard. Okay, so that's the derivation, and now I will switch to the presentation, and we will continue from here. Again, I usually at some point I decided to derive, because here again we refresh the idea of work in general. Again, this formula, scalar product, right? Then of course this It's good to practice from time to time, then because the more you practice, the better you remember and understand stuff. Okay, let's switch. That's what I just derived. Right? A few years ago, I used this slide, but it's too much of mathematics for slides, right? So usually, if it's too much of math, it's better to do it on the whiteboard. Now, the next system, you remember I told you that we're going to introduce potential energy for two systems. It's either point charge inside of a parallel plate capacitor, that's what we just discussed. And now next system are 2 point charges, right? Again, they're going to interact, of course, and of course we can introduce, we should be able to introduce potential energy. Derivation of the formula is very similar. We're not going to derive it because you see it's a little bit longer because you have to write more complicated formulas, right, expressions. But idea is the same. Again, you have a positive, okay, point charge Q capital, right, and then charge Q small. You take that Q small charge and move from initial point to the final, like what we've just done. But now mathematically it will be more complicated, right? Calculate work, then again recall from physics 1 this formula that W equals to minus delta U, and the same idea, slightly more complicated only. And as a result, the expression for the potential energy of 2 point charges Q small and Q capital equals K product of charges and divided by the first power of the distance between them. Right. Okay, so first of all, again, about the reference point. Where is the reference point? Because as I told you in the previous class, it's important once you introduce potential energy to mention where is the reference point. In this case, the most convenient reference point is at infinity. Because you remember what's so special about the reference point? It's a point where the potential energy equals to 0. In order to make this potential energy 0, R must go to infinity because R is in the denominator. Upstairs we have constants, right? But R is the variable, so if you go to infinity, potential energy will go to 0. So the reference point is at infinity. And usually it's the most convenient reference point if you have finite system in size, right? The most convenient point, reference point, is at infinity. Capacitor, like from the previous example, is not a finite system, right? You remember capacitor is constructed out of what? From the mathematical point of view, how did we introduce capacitor? We took an infinitely large charge surface, infinitely large. So it means that ends of the plates goes to infinity. So we took 2 of those plates and we brought them close to each other. So strictly speaking, it's not a finite system, but a system which edges of which goes to infinity. So in those cases, yeah, you can pick a different reference point, and we pick the point at the negative electrode. But usually, if the system is finite, like in this case, the most convenient point is at infinity. The same story with the gravitational potential energy, which you practice in physics 1. Okay, anyway, so now, can this potential energy be positive and can it be negative? Yes, it can have both. It can be both, right? So if we have 2 like charges, both charges positive or both charges negative, then of course potential energy is positive. But if charges are opposite, then of course potential energy is going to be negative. So remember that potential energy can be positive and negative, right? So now let's answer the question. Conceptual question for you. I like this question. Not my all-time favorite. In a few classes, I will show you my all-time favorite question. But I also like this question and give something like this on the exam among multiple choice questions. Right? So what do we have here? 2 point charges. You see positive charge, negative charge. they travel towards each other. And of course, they interact. Of course, we can introduce potential energy of their interaction. So, which statement about potential energy is correct? A. Okay, so let's imagine that this, for example, a level of 0 potential energy, right? So, in option A, positive potential energy becomes more positive, so it's growing. Option B, positive potential energy becomes less positive. C, negative potential energy, this is 0. Negative potential becomes more negative. Negative potential becomes less negative, so less negative, it means increases, right? And last option, positive potential energy becomes negative potential energy. Which statement is correct? I'll give you probably even more than a minute, right? Give it a try. Even I prepared a timer. Right. Again, the poll is in the chat. Since you didn't chat much, it's right there. Two-point charges. So of course we need to use the formula which we just derived. Okay, discussed, not derived, in the previous slide. So be careful which formula you use, because on the exam I see sometimes system is this, but the students use a formula about describing potential energy of a completely different system. Right. Okay, so anyway, so of course we can use this. Potential energy, it's a K times product of charges and divided by the distance between them. And first of all, what can you say about this potential energy in terms of a sign, in terms of the sign? Since charges are opposite, potential energy is negative, right? Potential energy is negative. It means that immediately option A talks about positive potential energy, out. Option B, again, talks about positive potential energy, out. Potential energy here cannot be positive. And option E, also positive potential energy, out. So 3 options are out, only 2 left, C and D. So now we need to find out what happens with the negative potential energy with time. Is it becoming more negative? It means it's going down, more negative, or less negative? It means it's growing, right? So now what happens with R, distance between these 2-point charges? R is going down, and R also is in the denominator. So it means that absolute value of the potential energy is growing. Again, absolute value. For now, I want to forget about the minus for a second. So absolute value of U is growing because R is going down. But now if we add minus, because potential energy is negative, growing, it means that potential energy becomes more and more negative. So it means that what option C is the correct one. Right. Wait, I need to bring up again slides forward. Right. So option C is the correct answer. Of course, we can have different configuration. We can have 2 negative charges, 2 positive charges, right? They can travel not along the same line, but in a more complicated. They can have a more complicated motion. But again, basically the same logic, the same speculations can be applied to analyze this system easily, right? Okay, so and this time your answers are spectacular, right? So distribution is awesome, right? Not like 2 classes ago.